Okay. We are dealing with Hilbert space of random variables, all possible random variables with the inner product, zero mean random variables with an inner product given by the correlation. And in general, the random variables are complex valued. That is, I am dealing with a Hilbert space over the field of complex numbers. Scalars that I will be using, they are in general complex. Okay. They are one particular problem we will be now studying, and that is the problem of linear prediction. This is related to optimal filter and adaptive filter, as it will slowly reveal. But to start with, let us see what is a linear, what is a linear prediction. Okay. Pth order linear prediction. Suppose in the optimal filter scenario, we had this thing, right? There was a sequence coming, we had a filter W vector, output was W vector H, the input here. Okay. If the input you say UN, then it is W, and there was a desired response. This is the error. The error was, we took the variance of the error, which was a second order function of all the weights. We minimized it. It gives only it is a quadratic function of the weights. So, obviously, it has a unique minima or maxima, and in this case, it is minima. You solve it, you get a filter expression. And since all the processes are stationary, jointly stationary and independently stationary also, the filter that comes out is independent of n, optimal filter. It does not depend on the time index n, that you have seen. In fact, the filter expression is R inverse P and all that we have seen. Okay. R is the autocorrelation matrix to the input, P is the cross correlation vector between Dn and Un vector, all those we know. Now, we also know the actual meaning of this geometric interpretation, that actually you are orthogonally projecting Dn in the space spanned by Un minus 1 up to some past terms Un minus P. Projection is unique. This is, so the projection coefficients are given by this. They combine them and you get the output. That output I call a filter output, but basically nothing but combining, linearly combining Un minus 1 up to Un minus P by some coefficients, so that the error norm square is minimized, and that error indeed will be orthogonal to each of Un minus 1, Un minus, that we have seen from our vector space point of view. Now, we will consider now a particular case where this Un is coming from one signal x n with a delay, and this is coming directly here. And how many, suppose we have got W equivalently what? W, say, in this case, let us put W 1 to W p, not W 0, so P coefficients. So, Un is nothing but x n minus 1. Okay. What is this optical filtering problem here then? You are estimating x n, okay, from what? X n minus 1, x n minus 2 up to x n minus p. So, orthogonally projecting x n on the space spanned by x n minus 1, x n minus 2 up to x n minus p. So, what you get is a linear combination of the past p samples, which is a good estimate of current sample. So, this estimate is called a linear prediction. That is the best possible in terms of vector space arrangement, vector space notions. This is the best estimate, because the corresponding error has the minimum norm square, and that will be orthogonal to all this x n minus 1, x n minus 2 up to x n minus p. So, this is a special case of the general optical filtering problem, where Dn and input are generated from some x n. But obviously, x n is nothing but, this is our linear prediction problem, because what you are doing is you are trying to estimate x n as a past combination of, as a combination of the past samples, or rather you are projecting x of n on the space spanned by x n minus 1, x n minus 2 dot 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 x n minus p. The linear combination comes out here, which is the prediction. This is the best prediction, because the corresponding error, this corresponds to orthogonal projection. The error is perpendicular, this orthogonal to all these terms, even x n minus 1, x n minus 2 up to x n minus p, and therefore, the error has minimum norm square. Norm square means variance. Fine. In this case, obviously, this combiner coefficients from stationarity, if you assume x n to be W y stationary and all that, we know from our from our earlier analysis what this expression for W is, that we know, that was the R inverse P. How R and P independent of n, how did that happen? Because of stationarity. So, in this case, you know one thing, that even though random variables here are x n minus 1, x n minus 2 up to x n minus p, they are all function of n. The thing that you are going to project, that is x n, that also is a function of n. The combiner coefficients, they are independent of n. So, whether at nth index or at mth index or kth index, whatever you do, you get the same combiner coefficients. That comes from stationarity, that we all know, this is beyond question now. Okay. That is why the combiner coefficients are independent of n. Okay. Now, keeping this in mind, now let me introduce some notations and notions rather. Okay. Suppose in that Hilbert space H, I consider a subspace WKP is a span of x n minus k, x n minus k minus 1 dot 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 x n minus p, and obviously k is less than equal to p. Some definitions I am now giving you, starting from past sample x n minus k to x n minus p, and k is of course less than equal to p, otherwise it has no meaning. If you take their span, call it WKP, that is a subspace of the Hilbert space H. So, this subspace has its own linear projection operator, a orthogonal projection operator. I told you for this subspace, I mean given this subspace, take any vector of H, there is any random variable, you can have an unique orthogonal projection of that on this, and that operation is linear. You remember I proved all this, that operation is linear. Okay. So, that operator also is unique, because it takes, if you take any vector, it gives you only one output, one component uniquely. So, that is a unique operator, isn't it? Anyway, so that I denote as this PKP as the orthogonal projection operator with respect to the given WKP. But I told you often instead of projection, rather in the case of lattice, in fact linear prediction and all, we will be more bothered about the error. Error is orthogonal to the subspace, we know. Error will be orthogonal to the subspace, but that error I want to find out. So, given an external random variable, say x, not x or y, whatever, PKP comma x, PKP working on y, or say y is a random variable, that will give you the projection. Projection will be a best linear combination of these elements. But I want to find out the error. The error will be orthogonal to them, having the minimum number square. That error operator is what? I will denote like this. Which is this actually I minus I is the identity operator. No matrix, nothing, just operator symbolically. What is this is called orthogonal projection error operator. We have done all this in previous classes. It will give you, if you work this on that external vector say y, this will give you the error. There is y minus the projection, fine, and that will be orthogonal to all these fellows who are spanning the space. I am of course assuming that none of the samples are linearly related. That is, this subspace has dimension equal to the total number of entry here. The samples of the random process, they are not any linearly related. There is no linear dependence relation. That is always there, implicit in all my treatment. No linear relation linking some samples of a random process. Okay, because in real life it hardly happens. This is the thing. Then I define two quantities. Please concentrate on all these. Pth order forward linear prediction error. I will explain. Please follow my notation. EPF, pth order forward error. Error means a linear prediction error at index n. It is nothing but, if you consider this error, can you tell me in terms of this notation what will that be? Because in this case, what is this error? You are projecting x n orthogonally on the space spanned by who? X n minus 1 to x n minus p. That means k is 1. So, the space is there is W 1 comma P. So, corresponding projection is P 1 comma P. Projection error is P 1 comma P perpendicular. That working on whom? Who is being projected? X n. Okay. If instead of E P F n I go for E P plus 1 F n, I will have to have one more term here, x n minus P minus 1, one more term I have to bring in, find out a projection, and that is what I will be doing, but I will be then orthogonally decomposing the subspaces, the subspace into 2, all those things I will do. Now, this is forward prediction. Why it is called forward prediction? Because very obviously from past you are looking at future prediction forward. This is a normal thing, you know, it makes at least some sense. That from past you are trying to, or from past up to present you are trying to find out the future. At least you get the coefficients, use them separately to combine x n minus 1 up to some term to predict about x n plus 1. Coefficients remain same. That has some sense. But now I will be doing another kind of prediction which does not appear to have any practical sense. But that is the key to everything. That is called backward prediction. Backward prediction means predicting some past term from the future of the past term including up to the current term. Okay. You can ask me what is the use? The past term is already available to us. Exactly. There is no, no need to, I agree. There is no need to estimate it, but still we will be doing it because of many reasons. One, that if you are interested to find out these projections for various values of P, 0, P equal to 1, P equal to 2, you need that as a secondary computation. You note those. Okay, but the more fundamental reason I will come to that, but first let me give you the definition. I am turning over the page. I hope you remember these notations. Please remember, because I cannot go on showing it, or maybe here only I can show. EPBN backward prediction pth order nth index. What you are doing here, you are taking, say, this candidate. You should see the notation. When it is EPFN, you should not get confused with the notation. So please see the notation, understand one for all. First, see whether it is F or B. F means forward, P means order, N is the current index. So that means take Xn as the guide to be projected or predicted, Xn, and on whom is the projection? Xn minus 1 to Xn minus P. But if it is EPBN, it is backward, then take the past quantity. What quantity? N minus P. That you project on is P future ones. What are the P future ones? Xn, you have to start at Xn, Xn minus 1 up to Xn minus P plus 1. Okay. That you do not try to understand what is the utility of that prediction. That we will see later. At least for this prediction, I need this prediction. Let me put it that way. Later you will see that these predictions actually will do Gram-Schmidt orthogonalization of the vector space. That is later, for which lattice will be used. EPBN then means, that means I am projecting this guy, say Xn minus P, onto whom? On the span of current 1. You have to always start at current 1. So see how to use this notation. N first is backward prediction. That means I have to go to a past term. Which past term? N is the current index. So N minus P. Xn minus P should be the term that should be projected into its P future ones. What are the P future ones? Xn okay. Okay. So in terms of our vector space notation, what is the space here? N minus 0. So k equal to 0 and P minus 1 here, W 0 comma P minus 1, isn't it? Or see the notation. What is N minus K? It was general case, N minus K to N minus P I took. What is K here? K is 0, N minus 0. What is P here? Instead of P I have N minus within bracket P minus 1, isn't it? So in this notation it is W 0 comma p minus 1, which means p 0 comma p minus 1, which means p 0 comma p minus 1 here. Okay. Don't get confused with this capital P and small p. They are two different things. I hope you understand. This projection operator, this is order. If you want, I can change this small p to anything else. But I hope you can see this. Is that okay? So that means this is equal to what? This is the error, not projection, but the corresponding error. Okay. Now, these errors are also random variables. So, I can have their variances also, which I will need in my development. So, I define the variance of this guy. My claim is that variance is independent of n. Why? Simply, what is this quantity? It is the projection error, means dn, that is xn minus the projection. Xn minus the projection. What is that projection? Is a linear combination of those elements xn minus 1, xn minus 2 up to xn minus p. But the linear combiner coefficients we already know, because of stationarity they are independent of n, isn't it? For any general case, you give a sequence here and you give some sequence something here, you get a linear combiner coefficient or filter, those are independent of n. That we have seen because of stationarity, we are also assuming stationary WSS thing. That means what is this quantity? It is xn minus a linear combination of past terms xn minus 1 to xn minus p, but the combiner coefficients are constants independent of n. That quantity I have to find its variance. So, I will take the mod and square, or the quantity multiplied by its conjugate, and there you now take all the terms, you will get lot of correlation terms, but because of stationarity all n will go from everywhere. Are you following me? I am not showing that, this is very, you should be able to visualize. I am writing this as xn minus linear combination of past terms xn minus 1, xn minus 2 up to xn minus p. Linear combiner coefficients are independent of n, that we have found out, we have seen in a general case. Now, this error I want to take its mod square or the error and multiply by its conjugate and take expectation operation. That is the correlation, that is the norm square definition in terms of our Hilbert space. Multiply a random variable with its conjugate, this mod square, take expected value. So, I take expected value. The moment I take expected value, there is norm square, there is variance. Because of stationarity of xn, all those terms, multiplying terms, they become independent of n, isn't it? You get some elements, I mean, where linear combiner coefficients will be present and correlation terms will be present, but nothing of n. So, that means norm square of this guy, there is variance of this guy also independent of n. So, in the notation, I can drop n, that is what I am saying. Notation I will be using sigma p, f, p and f goes as it is, but no n, and I put a square, because always like in a Gaussian case, instead of sigma is a sigma square, because it is variance after all. Just for that I put 2, this 2 is a notation, and this is what you can say E of square, which is also equivalent to norm square of this guy using vector space notation. By the same logic, I can denote its, I can take its variance also. Its variance also will be independent of n. After all, what is EPBN? You are giving here xn minus p, isn't it? Here xn minus p, that is all. But they are jointly stationary, this input is stationary, so obviously this filter will be independent of n and all that again, isn't it? And the same logic works. So, I give the notation sigma p b square, which is this E p b n square, that is expected value of mod square of this. Okay. Can you see up to this in the screen, up to this line? Now, gone. Okay. Now, suppose you know some way or other these two quantities, pth order forward and backward prediction errors, you know them, you know these quantities also, and I say get me the same quantities, at least to start with the errors, for p plus 1th order recursively. giving these 4 quantities, at least get me these 2 corresponding errors forward and backward for the next order p plus 1 h, and assume p to be at least equal to 1, so that there is, like here when you say p 1 comma p, if this small p is not 1, 1 comma 0 is meaningless here. You start at x minus 1. So, to start with, assume small p to be equal to 1 or higher. I will have to take the case of p equal to 0 also, that I will do later. That is, at least first order prediction errors are given to at least first order, that is p equal to 1. Okay. And you have to go for p plus 1, then p plus 2, p plus 3, like that, recursively. How to do that? To start with forward prediction error, I have to find out E p plus 1 f n. What is the corresponding subspace then? W 1. Forward prediction means it will always start at 1, but go up to p plus 1, isn't it? X n minus 1 dot 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 up to x n minus p minus 1. Okay. X n minus 1, it will go up to here, like x n minus 1 dot 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 this term and one more term. This space I will try to write as a orthogonal decomposition in terms of orthogonal decomposition, so that projection on that can be written as a summation of 2 projections. Now, how will I do that? Please see, I have given you this hint last time in the general case. This is my last entry. What I will do, otherwise this was already there, you have added one extra guy to this set. What I will do, space spanned by this, the span of total thing is what? Direct sum of space spanned by this much plus the span of this, because they are linearly independent, isn't it? You remember that way I told alpha 1 to alpha p, and then I bring some other factor beta. Overall space span by is what? Span of alpha 1 to alpha p, direct sum that of beta, but they are not orthogonal. But at least to start with, it will be same as space span by x n minus 1 to x n minus p, direct sum space span by this last guy, but they are not orthogonal. Then what I will do, this last guy I will try to project orthogonally on this, take the error. Then this will be equivalent to the space spanned by this set x n minus 1 to x n minus p, orthogonal sum the span of that error. There, those 2 spaces are equivalent, all those things we have seen last time. You remember? Last time we took the projection, we say the projection, this is contained in that subspace and that subspace is contained in this subspace, so both are equivalent. That kind of proof I gave. You remember, na? I took the general case, alpha 1 to alpha p, and then beta I brought in, span of alpha 1 to alpha p, direct sum beta, that is same as, that is contained in the space spanned by what? Span of alpha 1 to alpha p, orthogonal sum, projection of beta, projection error corresponding to what? Projection of beta on the previous space. You remember this I did, and I told repeatedly that this is what I will be using again and again. So, no question of explaining it. I will be simply orthogonally projecting this on the space spanned by this, take the error. So, the entire space will be what? Is orthogonal sum of the space spanned by this much, x n minus 1 to x n minus p. Then you can write that orthogonal sum and the span of the error. That is W 1 p plus 1, which is span of and this new guy, this is same as, you can write one line, it is the same as is the span of this, direct sum span of this element, but that I am skipping. That is equivalent to what? Span of this fellow, that is x n minus 2 x n minus p, which is nothing but W 1 comma p. Then orthogonal projection of this space, that is p 1 p perpendicular span of this. And I told you, when there is a single element, instead of writing span of that element, I will use this notation. You remember this also I said. This is not inner product. Inner product means after this there is a comma, two elements a comma b, x comma y. This is not inner product. I am using only these two less than and greater than symbols. This for once you understand, this is nothing but a new notation for indicating span of the single element. This notation I used in the last class to indicate, instead of writing the span thing again and again, whenever you have single element, I shall just put to these two lines less than and greater than, and it will mean the same thing, span of this guy. Now, question is, what is this? Now, suppose n minus 1 you call n prime, n minus 1 you call n prime, then that means what? This is x n prime minus 1 up to n prime minus p plus 1 and n prime minus p. So, this is projecting x n prime minus p into its p future terms and the error. So, it is pth order backward prediction error, but at what index of time? At n prime index of time. What is n prime? N minus 1. By this definition, n prime minus 0, n prime minus 1 dot 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 n prime minus p plus 1. Those are the elements. On that n prime minus p, that is projected at the error, isn't it? Not understanding. I am calling n minus 1 as n prime. Then x n prime is what? N prime minus 0, then n prime minus 1 dot 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 n prime minus p plus 1 and n prime minus p. This I am projecting on this part. That means n prime minus p is projected on space spanned by what? N prime minus 0, n prime minus 1, n prime minus p plus 1. This one. What is projected? N prime minus p. So, what do you get here? E p b n prime, and n prime is n minus 1. So, this random sequence, if you delay by 1, that is what you get. This is a random variable at n equal to 0, n equal to 1, equal everywhere at every index is a random variable. You can form a sequence of it. If you delay that, then you get the next one, n minus 1, that way. Okay. Are you getting me or not? That means this is so my purpose was to find out E p plus 1 f n, right? Then you gave me the prediction errors up to pth stage, pth order. Why not get the same thing for p plus 1th? And what is E plus p plus 1 f n? It is p 1 this space index n with respect to n 1 means n minus 1, n minus 2 up to n minus p minus 1. These are what you have to find out. There is the x n fellow has to be orthogonally projected on this total span, but this space is orthogonally decomposed as, you can, if you want, you can put the orthogonal here, but I drop this. These two are mutually orthogonal, right? So, x n projected on this is what? What is the total projection? X n projected on this plus on this, but this is not projection, this is error. So, I have to take this, compute this projection, subtract it from x n. So, this is what? X n minus and what is this projection? Projection on this and projection on this. Projection on this means I will go only up to this. X n projected on the how many passed? Only p passed, x n minus 1 to x n minus p. So, that will give me pth order forward prediction error, not p plus 1th, isn't it? This projection I can write as, for your sake, I will do like step by step for once only. This projection you can write as summation of two components, projection on this, projection on this. Projection on this is what? Plus projection on the orthogonal component. This you know, projection on orthogonal component is what? On any vector projected on any another vector, you know the what that is. X projected on, say y projected on x, You remember I did this, that gross P orthogonalization, all those things. Y inner product with x divided by norm square of x. This times that vector x. I did all that keeping this in mind. I didn't do this just to teach you some mathematics. I told you repeatedly I will be using those things from now on. You follow this, y with x divided by norm y inner product with x divided by norm square of x. That is the coefficient, that times x. That means xn, what is the projection on this subspace? Xn inner product with this guy divided by the norm square of this guy into this guy. Okay. Into this guy. Now xn minus this is the orthogonal, this is a forward projection error for pth order only. This is very easy to see. This total space I am decomposing as what? This much, span of this much plus another extra component coming due to the projection. So xn projected on this remains the good old pth order projection error only. In this there is no change, there is this part, and that you subtract from xn, so you get the projection error. But essential thing is here. Here you see the denominator. What is the denominator? Norm square of backward projection error. I told you backward projection norm does not depend on the index because of stationarity. Didn't I tell you this? This is independent of n. Only this p, b, they matter, isn't it? So this n square will have no meaning there. So the denominator will have sigma p b square. This quantity will be as it is. Here xn with this, and what is this quantity? This is after all what? This is a projection of this last fellow on the space spanned by this part. So I can write it that way: p1 comma p orthogonal x n minus p minus 1, isn't it? So x n comma that. And remember I told you, I showed some fantastic thing last time, that whenever you have this operator, you can interchange the operator x n comma this projection or projection error operator working on another vector. You can pull it, you can either repeat it on both, or you can take it from here and push it here. You understand? What was the logic? Logic was xn can be written as a what? Xn itself can be written as what? Summation of two components, projection on this space and the error. Projection on that space and error. Projection and this, they are mutually orthogonal. So that goes, only the error part. Error part means again p1 p orthogonal xn. So p1 comma p orthogonal xn. So this operator gets repeated twice. Then I can drop this operator. Why? Because this can be written as original vector xn minus p minus 1 minus the projection. But that projection is orthogonal with the error component coming from here. See, this is repetition, this I explained. If you do not follow, I cannot help. I took pains to explain all this in the previous, I am only reminding you. I told you that time that please remember this always, all throughout the course, I will be making repetitive use of this. Okay. So I will be bringing it from here on top of it xn. And the moment I bring p1 p orthogonal on xn, I get back this xn of projected on this part and error. That is our good old pth order forward projection error. So inner product between pth order forward projection error of nth index, pth order backward projection error of n minus 1th index, and inner product means correlation. And this inner product I will define as, again this inner product. Okay. So that will turn out to be this quantity. This quantity will be what? Inner product in fact I am not taking, I am only repeating this, I am leaving as it is. This is P 1 P orthogonal x n minus P minus 1 as it is, this I can repeat on this. So, this remains error and this comes on top of it also. So, this becomes another error. This remains as it is, which is equivalent to EPFN. Okay. Now, please see what is this? It is the inner product. Inner product means correlation between the two. What is the correlation? That is expected value of this into conjugate of this. What is this? It is x n minus a linear combination of these past two elements. Combiner coefficients are independent of n. Projection same here, and you are multiplying. So, again correlation terms will be free of n after you apply the E operator. So, this net quantity again will be independent of n because of stationarity. Are you following? EPFN is what? X n minus a linear combination of these fellows. So, you have got terms like x n minus 1, x n minus p, all that. Similar kind of thing will be here, and you are multiplying the two. So, you will have only many correlation terms. All after E operation, you will get correlation terms. So, they are all independent of n, only a gap, lag. So, this entire quantity is independent of n, time invariant. I can give it a name, pth order, so it will depend only on p, but not on n. I can call it delta p. It is called partial correlation coefficient, PARCOR, we call it PARCOR, partial correlation coefficient, PARCOR, PARCOR. So, this is your delta p. So, you see this is one recursive relation. Given this fellow and this fellow, that is pth order forward prediction error and pth order for the past, not even current. I can find out p plus 1th order forward prediction error for the past, for the current index. But I need to update this also. Unless I update this, how can I from here go to p plus 2? Because that time I will require EP plus 1 B n minus 1. Isn't it? Are you following me? If I have to from giving these two, I could obtain this. Then again, how to get EP plus 2? Then I have to be given EP plus 1 Fn, EP plus 1 B n minus 1. That means I must update this in P also. Okay, I will apply the similar, absolutely similar philosophy, just little change of terms. I mean, here the space consists of some terms, there the space will consist of extra term and will not consist of particular term like that, but philosophy is same. So, now I will go for EP plus 1 Bn. This relation you remember, huh? This is my relation. This one half of a lattice filter, lattice stage. Now, I go for EP plus 1 Bn. What is EP plus 1 Bn in case you have forgotten? EP Bn means go to the past term n minus p and then look at the p future terms including current. So, n minus 0, n minus 1 up to n minus p plus 1. This span space, on that I project x n minus p. So, now I am going for this. So, that means I have to consider n minus p minus 1, isn't it? That is, I have to consider this projected on from current, that is 0 delay, to pth. N minus 0, n minus 1 up to n minus p. So, total p plus 1 terms. Those are the p plus 1 future terms if you are standing at this index, isn't it? N minus p minus 1. So, immediate future is n minus p, then n minus p plus 1, then n minus p plus 2, dot dot dot, then n minus 2, n minus 1, n minus 0. This span space, on that I project this, take the error, that is my p plus 1th order backward prediction error. What is the space here then? W0p, this is a projection. So, here W0p, here one term I will take out. I will take out one term as the new guy. Which term? This term or this term? Between the two I will take out Obviously, first I will say it is a direct sum. This space is the direction of span of that single guy and the rest, and then I will project that guy onto the rest and take the error. So, I will have an orthogonal decomposition. So, should I proceed with here or here? Does not matter. It matters because my this element is to the right of this. If I take this out, I am at a loss. There is a gap, isn't it? A minus p minus. I take this out, and if I project this on this part, I again get back my pth order forward projection error, all that. N projected on this part, n minus 1 to n minus p, isn't it? This is same as what? Span of x n direct sum span of this rest. If you want, you can write this way: x n span of this remaining part, that is W 1 to P, W 1 to P and this x n. But this is they are not orthogonal. So, I will be projecting or x n orthogonally on this and take the error. So, then this direct sum becomes orthogonal sum. If I project x n on this part, what is the error? After all, x n projected on what? X n minus 1 to x n minus p, the space of that. The error, that is forward projection error, pth order. That is now this fellow is to be projected on this together. That means on this plus this, because it is orthogonal decomposition. At least this fellow, when projected on this part, so that means what I have to do, E p plus 1 b n, I repeat from here, it means this error original fellow minus the projection that is projecting this guy on the space spanned by this projection subtracted from the original one, that is the error. I am writing, and this projection can be written as what? This much, a projection on this part, projection on this part, summation. First projection on this part, and here x n comma, mind you, x n comma this, not this comma this. When y is projected on x, it is inner product between y and x divided by mod x square, not x and y. Two things are not same when it is a complex. One is the conjugate of each other. So, do not be casual and say, oh, a comma b and b comma are same. No. So, x n projected on this. So, x n with this guy inner product divided by norm square of this guy into this guy. Pretty simple, projected on this, x n with this by norm square divided by norm square into this guy. Now, here again n minus 1 if you call n prime, then look at only this part. After all, p 1 comma p, what I am doing? I am taking one part here, another part projection. I am projecting on that an error. That error is this, and net projection is what? One projection I have to find out the span on the spans spanned by this. But there, if I take n minus 1 to be n prime, then x n prime minus 1 up to n prime minus p plus 1, and this guy is n prime minus p. So, n prime minus p is projected on the space spanned by its p future ones. So, actually it is pth order backward projection error for index n prime, and this becomes error. When you back home, please see these derivations. You will see it is just in one case one subspace gets an extra element from the right side, here it is from the left side. It is just that, nothing much. N prime is n minus 1, so I am substituting in minus this. Again, I will play the same trick here. If f n is p 1 p perpendicular x n, p 1 p perpendicular x n, this I can repeat on this. Just a minute, this is not x n, this fellow is projected. I made a mistake. This is here you will have the guy who is projected is this guy, na? I am projecting this on the space on this together. So, this on this plus this on this. This on this is inner product between this guy and this guy divided by the norm square of this guy into this fellow. Isn't it? Because fellow who is projected is this fellow. So, I have to take the inner product between this fellow and this fellow, take the divide it by the norm square of this into this. So, this n minus p minus 1 here, and p 1 p perpendicular I can repeat on this. And what is p 1 p perpendicular? We have just now seen what is p 1 p. P 1 p, that this space only 1 p, na? P 1 p means x n minus 1 to x n minus p, x n minus 2 x n minus p. E p b n minus 1, this much, on this you are projecting this. So, again the same thing, pth order, I mean if you can call n minus 1 to be n prime, so n prime minus p and n prime minus 0, n prime minus 1 and n prime minus p plus 1 that way, isn't it? So, p number of future terms studying at, when you are studying at standing at n prime, you are looking at p future terms, on that you are projecting. So, pth order backward prediction error, but because you are projecting backward from using future you are projecting back. Okay. Pth order backward prediction error for index n prime which is equal to n minus 1. So, that means this becomes inner product of divided by this norm square we know, this is a variance of this, and that is independent of n because of stationarity, or that is using our notation into EPFN. So, this is the another relation. So, these are the two relations. One was this, here I called it delta p. What was delta p? EPFN and EPB n minus 1, they are inner product. Here is a reverse. So, it is delta p star, this quantity is delta p star. Okay. We will show that sigma p f square and sigma p b square they are same. We will prove it using induction and stationarity. We will prove. The numerator, these two quantities may be different. One is sigma p, the variance of backward prediction error, and this variance of forward prediction error of the same order, but they are same. That we will see. And both are real, because variance after all, both are real. So, only difference is in the numerator. Numerator is complex because inner product is not necessarily a real number between x, but one is the conjugate of each other, the other. So, that means this overall multiplier in one recursion is the conjugate of the corresponding multiplier in another recursion. I can draw a circuit, a stage now.
All the properties of xn remain the same if we reverse the sequence, right? Then why do you have to prove that variance thing? If we reverse xn, then we are doing the backward prediction itself, right? Like now we are using n to predict n plus 1. If we reverse the thing.
No, that I mean you are saying intuitively. There is no, I mean, I don't know how you can arrive at that.
At least the variance thing we can arrive. Because
if I lift the notion of stationarity, they are not, but using your line of logic, they are always. It is only true for stationarity. But the way you are putting it, that should be applicable whether it is stationary or non-stationary.
But I think we have come till now itself using stationarity.
That is okay. Stationarity I have used where? I am only making them independent of n, that is all.
So, to prove the equality of variance, we need stationarity.
We need stationarity. Anyway, so first start with this guy, forward prediction, p plus 1th order, it takes EPFN, EPFN minus a quantity, this whole quantity I will call it Kp, Kp is called the reflection coefficient. Kp, reflection coefficient. Denominator is real, numerator is in general complex, Kp. Kp times this backward, sorry, this is n, so this is n minus 1. But independent of n because of stationarity, and you get, this is for p greater than or equal to 1, mind you. Initially I told p minimum value take to be 1, but this will work also for p equal to 0, that we will see. And now this other one, Ep plus 1 Bn, again it uses the same two signals, Epfn, Epbn minus 1, but multiplies in a different way. This quantity, I told the denominators are same, but I have not proved it yet. So, this whole multiplier I call it Kp prime now. Later I will show that one is the conjugate of other, no point. So, you in giving a new name. So, this entire quantity let us call Kp prime. So, this will be this one stage of lattice filter. Okay, delay I put here, and you can cascade it. When you cascade, this is Ep plus 1 Bn na. This start with the delayed version, that is why delay. I am putting the delay on the input. If you take this and go on cascading it, you will get various orders. We will show in the next class that both these variances are same. Then Kp prime are same, that one is the conjugate of the other, obviously. If their denominators are same, numerators are already conjugate of each other, delta p and delta p star. So, together they are conjugate of each other, because denominator is not only same, they are real. And then an important thing is this reflection coefficient, their magnitude is always less than 1. That will prove. Okay. Using that, we will show that if you can use the, if you want to use the this lattice filter, we will develop the entire lattice filter for doing something like, auto regressive modeling. You know something about this, na? Did I discuss in this course? Power spectrum estimation, air modeling and all that. Okay, I will do fair bit of that also. So, their stability of the filter will be guaranteed because of this fact that the reflection coefficients have magnitude less than 1. We will get a not only causal and stable filters and all those. Again, DSP and other things will come up. So, it is not just vector space, they will be integrated related now from now on. So, that is all for today. So, see you then. Thank you.